The AEV began using similar structures to the final AEV. With the crosspiece as the central body and using winglets to attach propellers on the sides, it was assured the AEV would have good balance. The main issue with the preliminary design was the necessary central wheel chassis, which was impossible to use in practice. Along with this problem, the raised propellers would have interfered with the track, making it an impractical and impossible design. The second design had lowered and flared out winglets, which allowed the propellers to be further away from the center of the body, as well as not interfering with the monorail. This design element would allow for the design and implementation of a hard cover, which could be used to further increase protection of the Arduino, as well as managing cables. The offset battery design also shifted the center of mass to just below the wheel chassis. The next design the team evaluated was more of a test vehicle. The team wanted to know how placement of the fans vertically affected efficiency. Keeping the design essentially the same allowed the team to test this idea. After testing, however, the team could see no difference in efficiency between the original design. The final AEV was the continuation of the second design. Utilizing a hard cover, the AEV became more durable, better managed, and better balanced. By shifting the center of mass down, the AEV took turns even better than before. Although not expected, this was a positive secondary outcome of the hard cover. The hard cover, weighing approximately 50 grams, was the final piece of the AEV added before final testing. During the final test, the AEV had an undercharged battery. It did not affect its performance in many areas except one. As the AEV moved up the second hill, it stopped short of the observation area. This did not hinder it from completing its mission, however. As you can see, it stopped at the drop-off point perfectly fine. The AEV performed its mission successfully and accurately, proving that it had the ability to accomplish the goals laid out in the MCR. But how did it perform in terms of energy use? The movement of the AEV was split up into 5 main phases. The energy from these phases was calculated and put on this chart. 324 joules were used in the total run, and 102 in the highest consumption phase. The highest consumption phase happened near the end of the test, while the AEV moved back around the curve. A combination of worse efficiencies moving backwards and the largest distance needing to be traveled in one phase contributed to this result. The power time plot, as shown here, has several high spikes. Usually near the end of the phase, these spikes indicate areas where the AEV halted itself using a motor speed function. The double spiked phase around time equals 40 seconds was the point where the AEV was at the top of the second incline. These double spikes are in line with the high power used to get the AEV over a small piece of tape. Shortly after getting over the tape, the AEV returns to a smaller power consumption. The largest power phase is clearly visible around time equals 50 seconds. This was the move to cart origin phase from the phase breakdown. In conclusion, the team's AEV performed with good accuracy, efficiency, and precision. The team was able to overcome several real-world issues such as time management and communication. Through these problem-solving techniques, the team learned a lot about the design process.